Hi, I thought I would do a quick review of magnetostatics and electrostatics. We've covered a lot of material, and it may be worthwhile just to look at it and try to pull out the big ideas from what we covered. This might be useful, for example, if you're studying for a test and don't want to go through all the lectures. The first thing we covered was the idea of electric charge as expressed through Coulomb's law, which is given right here. We have a charge, let's call it Q sub A. And this charge Q sub A puts out an electric field, and we know the electric field extends away from the charge in all directions. If we want to know what the electric field is at some point here, we basically say the charge is located at position RQ, that's a vector, the point we're measuring it is Rm, and then this expression gives Coulomb's law right here. It's vector, it gives rise to a vector field, it's very complicated. If we have another charge here, QB, it's going to feel a force. It's basically determined by the size of the charge QB and the electric field created by charge QA. Another thing to note with electrostatics is that the charge in coulombs, even though it's a very small number, is actually very big compared to the mass of the electron, which is about 9 times 10 to the minus 31 kilograms. And so essentially the big ideas are that charges are a property of matter, or charge is a property of matter that gives rise to all electrical and magnetic phenomena. Because of the small mass of electrons, which are the charges that can move, and even the relatively small mass of protons, charges can exert very big forces on other charges, and that charges create vector force fields. So let's look into this a little bit more. A key idea is that electric forces can be very strong. You don't see strong electric forces in daily life because of something called charge neutrality, which is because charges are mobile, especially electrons, and they exert great forces on one another. They tend to clump together in equal amounts, so you have an equal amount of positive and negative charges. So let's do a thought experiment. But let's basically flow some current into a 100-watt light bulb. That's basically a standard incandescent bulb. Since we're putting 100 volts at 1 amp into this light bulb, we're going to collect about 1 amp or 1 coulomb per second, which is about 6.25 times 10 to the 19th electrons. If you go ahead and calculate the electric field put out by Q being 1 coulomb of charge, and use the value epsilon naught, the permittivity of free space, you find out that the electric field is 1,000,000 volts per meter up to 95 meters away from this collection of 1 coulomb in charge. Since about 1,000,000 volts per meter is what it takes to ionize air, what's caused in lightning, you essentially get lightning bolts from this charge that would extend out almost the length of a football field away if we could accumulate all this charge in one space. If we use the force law, which is given right here, it's just the second charge times the electric field put out by the first charge, and we put two charges, each of 1 coulomb, about 100 meters apart, you'd find that there were 200,000 pounds of force pushing these two charges apart. What this means is that electrical forces can be amazingly strong, but because of charge neutrality, we don't see this in everyday life, and we don't really appreciate it much. The other idea is that charge is a vector field. It's a little bit hard to see, but if you have a charge Q here in the center of the screen, given by the red dot, it creates electric fields going out in all directions, and essentially what it does is a vector field maps a vector, an arrow with both a length and a direction, to every single point in space. And this is what the vector field of a single charge would look like. And every time you see a notation that looks like this, basically you have a vector given as a function of another vector. It essentially is telling you the mathematical expression is creating a vector field. The next big idea we covered was that of superposition. Superposition says that electric fields add linearly. So the idea is if we have a charge 1 here, there's the red dot, charge 2, the yellow dot, charge 3, the green dot. Each of these is going to create an electric field at some point P out here in space. The red dot is going to create an electric field in that way, the yellow dot in that way, the green dot in that way, because they're all going to push away from the charges. The electric fields always point away from charges. But the overall electric field at point P is just the sum of these three vectors, or will be a vector basically pointing out in that direction. In other words, if you have a lot of charges, there aren't a lot of different electric fields. There's only one electric field, and that electric field is a sum of the individual electric fields put out by charges. And that we call the principle of superposition. The general idea here is that we can sum up discrete charges to get the overall electric field, or if you have something more like a distribution of charges, very, very tiny chunks of charge, we can sum up a line of the charges, all the charges over a surface, or all the charges over a volume to get the overall electric field. And this leads us to do some sort of integrals that can get nasty for a lot of problems because we have basically quantities with vectors in both the numerator and the denominator. But in many cases, for standard objects, these problems are solved and you just look up the answer. The idea? Superposition means we can sum up electric fields from multiple charges to give us the overall electric field at a point. The next of our big ideas is to define the electric potential of the voltage. And the voltage put out by a charge is related to the potential energy that a second charge sees in an electric field. So let's say we have a charge Q sub A right here. We know it's going to create an electric field that points in all directions. It maps a vector to every point in space. If we take a second charge, Q sub B, and put it right here and think about moving this charge Q sub B toward the first charge, we can calculate the force on that second charge, first by assuming the first charge QA is at the origin, and we only consider the x-axis, so we do a one-dimensional problem. So the electric field simplifies there. The force, of course, is given by that expression. We've already covered that. So it's fairly easy to calculate the force on the second charge. Well, we know essentially that energy, as a function of distance, we simply have to integrate out from infinity, where there's going to be no force on the charge because it's infinitely far away, to whatever position x naught we bring the second charge to. When we do this, we can essentially find the potential, the amount of potential energy that this charge has. And the potential energy, or the potential energy field, is given by this expression right here. It turns out that the overall energy of charge QB is the charge QB multiplied by the voltage we calculated in this case. Why is this important? Why do we care about this? Well, it turns out that besides creating a vector field at every point in space, a charge or distribution of charges creates a scalar field at every point in space. And this scalar field is a potential energy field created by the charge or distribution of charges. And it turns out that just like the vectors add linearly due to superposition, the voltage or potential energy fields will also add linearly in most cases due to superposition. So we can calculate the voltage from a charge or distribution of charges by simply summing up the charges, doing line integrals, surface integrals, or, as not shown here, a volume integral. The reason this is important is instead of having a vector in the numerator and a vector quantity cubed in the denominator, this is a much simpler integral to do, so it helps many times to calculate the potential rather than the electric field from a distribution of charges. And these three quantities, the charge, the electric field, or as we'll soon talk about, the electric flux, and the potential energy created by charges, the voltage, define our trifecta of electricity, if you will. The charge is a fundamental property of matter, kind of like things have mass. Some particles have charge, and it only affects things that have the same property. Charges only affect other charges, just like particles with mass only exert gravitational forces on other things that have mass. Fields are vector fields that are created by charges. You can think of them as invisible force fields that push on other charges, and the flux d is the amount per unit area of the force rays. It turns out the voltage is simply the potential energy created by charges. It's a scalar field, and it's essentially, you can determine the energy from the voltage simply by multiplying the voltage by the amount of charge. So it essentially tells how much energy a charge will have in a scalar field. And although I'm not going to cover it in depth here, one of the key ideas in electrostatics is there are relationships between fields and fluxes, charges and voltages that are very well-defined mathematical relationships that involve both integral and differential operators, and so we can convert either way, from a charge to a field to a voltage to a charge, depending on the types of operations we choose to do. And these are shown in the diagram right here. If you look at the operators on the inside of what I'm calling the electrostatic triangle here, you see we need to define several different differential operators in vector space. This term here is called a gradient, this one's called a divergence, and essentially this del squared operator is going to give us Laplaces and Poisson's law. So let's take a look quickly. The gradient of a scalar field essentially turns a scalar field into a vector field. And the vector field that's created points in the direction of the maximum rate of change of the scalar field, with the magnitude equal to the spatial rate of change. And here's essentially a scalar field that I generated. I'm plotting as a three-dimensional surface, so you can see that there are higher values here in our scalar field at the peak values near 1. The lowest values of this scalar field are at this point in space, and you can see by the colors looking at the scale over here that they have values of -1. And I did this in MATLAB. This is a fairly easy thing to create using that code right there. The definition of a gradient mathematically is given right there. So using this expression for the scalar field, if you take the gradient of it, it gives you a vector field, the rate of change of x in the x direction and the rate of change in the y direction. You can see I've overlaid on top of a contour plot showing the positive values and negative values of that scalar field as concentric colored circles, the gradient. So you can see that the gradient, the vector field, essentially points uphill from the lowest values to the highest, and the arrows always point at the steepest part of the slope. They always point to the maximum rate of change. And again, this expression right here is the overall expression for a gradient. Another one of the big ideas we covered was something called Gauss's Law. And Gauss's Law says the flux, or the number of arrows per unit area, through any surface is related to the charge inside the surface. So if you look at box 1 here, box 2 over here, box 3 over here, you can see that arrows pretty much go through it. There are equal number of arrows entering as leaving each of the boxes, so the overall flux going through these is equal to 0. There's the same amount entering as there is exiting. But if you look at box number 4 that contains the charge, it's pretty obvious from this diagram that all the arrows are leaving. And so you essentially have the flux in Gauss's law being equal to the charge enclosed. And so a way we write this is we say the flux vector d dotted with the normal to the surface ds is equal to the charge enclosed, which is simply just the volume integral of the charge density right there. And this, in effect, is the integral expression of Gauss's law. The total amount of flux going through any closed surface is the amount of charge enclosed within that surface. It turns out that the vector differential operation called divergence is a differential form of Gauss's law. The divergence, written as del dot, a vector, creates a scalar field. So a divergence turns a vector field into a scalar field. And the value of that scalar tells you whether a point in space is either a source or a sink of flux lines. And this is the expression to calculate divergence right here. It's just basically the x integral, the y integral. No, that's not right. It's basically the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component over some volume element. And essentially what this tells you is within any tiny volume element, if you have more flux rays going into the volume than you have going out, you essentially have a positive value of the divergence. If all the flux rays go through and none start there and none end in it, as in this case, the overall divergence is going to be 0. If you have flux rays exiting and not entering, you end up with a positive number for the divergence. So basically the divergence of the flux d will tell you whether or not there's charge at that location and whether it's a positive charge or a negative charge when you have a charge distributed over a volume. The third set of differential operations that relate charge to voltage, to field, or to flux was Laplace's and Poisson's equation. They relate the potential to the charge. The form of Laplace's equation particularly makes it very easy to do numerical iterative approximations, as we'll see in a minute. And so essentially what we're doing is we're just taking the gradient of the divergence, and what we come up with is an expression that looks like that using the del squared operator. The del squared of the potential happens to be equal to the volume charge density divided by epsilon with a negative sign in front of it. That's called Poisson's equation. And if you have a region of space, as most regions are that don't contain free charge, then this term right here is equal to 0, and we call that Laplace's equation. And it turns out you can solve Laplace's equation numerically easily. The procedure to do this is to define some potential in the region or on the borders. This becomes a boundary value problem. And essentially what you're going to do is you're going to move this calculation cell across this array array to make a best guess or an estimate of the potentials at each point. And once you've gone through the whole thing, as we saw in the video, you get a first guess, and then you just repeat the process, moving this calculation cell through the array again, and you get better and better guesses. And so essentially you just keep repeating this procedure until the values you get don't change very much. You hit a maximum number of iterations and say, okay, this thing isn't converging, or it's not converging fast enough, or you basically call it and say, okay, this approximation isn't going to converge. It turns out that this is extraordinarily tedious to do by hand, because you've got to have very fine grid cells, but computers do it very well, and there are a lot of professional packages that will do this for you. Generic numerical software like MATLAB, for example, or Mathematica can do this fairly easily, and you can also do this in Excel. And if you're in my class, we did several examples of using Excel to calculate the potential in a region. So very briefly, that pretty much covers some of the mathematics and differential relations that relate charge to field and flux to the potential of the voltage. Another thing we covered, and another key idea, was that the electric field is affected by insulating materials or dielectric materials. So essentially what we have is we have some charge Q there that puts out this vector field, this array of electric field vectors or flux vectors, and we're going to look very closely, that's what the magnifying glass here represents, at some insulating material that has a permittivity epsilon. As we saw, what happens is that when the electric field goes into the material, generally the atom cores that have a positive charge stay fixed, and you get a deformation of the cloud of electrons. You get a net negative charge, because these electric field vectors, E here, those are the black arrows, are going to pull the electrons toward them. And what this results in is a net negative charge on one side of the dielectric material, that's these green circles, a net positive charge on the other side. And then we defined another vector called the polarization, and we used the expression P for it, and it's shown by the blue arrows, that points opposite to the direction you'd think, so it can be pointing in the direction of the electric field. So what happens is electric fields create polarization inside material. It turns out that there are a lot of relationships between the flux vector, chi, that we call the susceptibility, the overall permittivity epsilon, the relative permittivity epsilon r, and the polarization P. This gives all the various expressions and ways to relate the flux vector to the electric field vector, and generally they're related through epsilon. It turns out that you use this when you're calculating material properties, but for most cases we use the relative permittivity, and we simply say the flux vector D is epsilon naught, the permittivity of free space, times the relative permittivity times the electric field. The key ideas in this are that insulating materials or dielectrics respond to electric fields by creating an internal opposing field due to some slight distortion of the electron clouds. If you have a material made of molecules where the electrons can more freely move, they generally have higher permittivity, and this means that the force field, the force vectors, the electric field vectors, are reduced in materials at high permittivity, but the electric flux vector D is independent of the types of materials, so you don't have to worry about permittivity if you're dealing with D. And D is essentially the flux vector density, how many flux rays there are from a charge per unit area. Another one of the key ideas we talked about was that electric fields can change when they hit the surface of dielectric or insulating materials. We can always break electric fields into the component vectors, and if we do that for electric fields hitting a boundary where we maybe have epsilon 1 on one side and epsilon 2 on the other, materials with two different permittivities, it turns out that we can break this into electric field vectors that are parallel to the surface and those that are perpendicular to the surface. The components of the electric field vectors that are parallel to the surface on both sides of the boundary are the same. However, the ones that are perpendicular vary by the permittivity epsilon. And essentially what this means is that you can get a bending of electric field lines when they hit a dielectric material. And this is called boundary conditions. These are very useful for solving all kinds of problems. And the general idea behind this is you simply take the incident electric field vector, break it into parallel and perpendicular components, and use these expressions here to see how the two components change, and then you assemble it on the other side of the boundary. Well, all this mathematics doesn't really lead us to a happy place if we actually have to do electrical engineering, because it would be a real hassle if we were ever building a circuit and we had to do a bunch of differential operators or we had to do an integral to build every circuit. So what electrical engineers have done is they've sort of taken aggregate properties of circuits and described these aggregate properties, these distributed properties, in other terms that are sort of independent of the particular structure. And one of the key ideas for this is the idea of capacitance. And it turns out that capacitance is a property of an electrical structure that relates the amount of charge this structure can hold to the voltage you put across it. And this depends really not on the charge or the voltage itself, because the ratio stays the same. It just depends on the geometry of the structure and the materials that are used. And so all electrical structures that have conducting elements and dielectric elements, which can include air or vacuum, have this distributed property of capacitance. And capacitance is very different than a capacitor. A capacitor is an electrical device that's designed to have a specific capacitance, while any conducting structure is going to have some sort of capacitance whether you want it to or not. So in general, if we have two conductors, one conductor over here that has a positive charge, a second conductor over here that has a negative charge, and maybe we have some dielectric or insulating material between it, the capacitance is going to depend on the specific geometry and types of materials we have in this structure. And we define the capacitance as the charge held by these two insulating structures divided by the voltage. And we saw that we could calculate that, at least we can calculate the charge, by using Gauss's law, simply doing a closed line integral or surface integral, of the electric field given by the numerator of this expression, and the voltage, of course, we simply know is the line integral between the two structures. And so if we know the electric field of any structure, or if we can calculate that, we can determine what the capacitance is by performing these two integrals. We know that the charge is essentially the capacitance times the voltage. That's given by definition. And if we basically take the time derivative of charge, we end up with current. We take the time derivative of voltage, and we can write it like that. And we can essentially extract our basic circuit equation from this definition of capacitance. In many situations, we want to build a structure that has a maximum capacitance. For example, we want to store the most charge for the smallest voltage for maybe an application like energy storage. The most common way to do this is with a parallel plate capacitor. This happens to be the expression right here for a parallel plate capacitor, where epsilon is the material between the plates, A is the area of the plates, and D is the spacing between the plates. You can look that up in any book. And it turns out that you can have very, very large areas and close spacings, which are going to maximize your capacitance. Typically what you do is you get two metal plates, have a very thin layer of insulator between them, and roll it up like a jelly roll. So you have a very high surface area to volume ratio to maximize the capacitance, to store energy, or to essentially create a capacitance of a particular value, a capacitor of a particular value. It turns out, however, that capacitance isn't always a good thing, since any two conductors are coupled together by some sort of capacitance. If you have a signal on one conductor, you can actually couple that signal onto the other. So you look at the case of a wire 1 that essentially had a voltage pulse. Maybe we're sending some kind of digital signal, as shown in this diagram right here, and the voltage is varying as a function of time. Well, we know from our basic circuit expressions that if you have two structures that are coupled with an electric field and form some kind of capacitive structure, and so here's our electric field that's coupling these two structures, that the time derivative of the voltage is going to induce a current on the second wire. So you may get a very small current on the second wire that has a structure like that, and you essentially have a positive going peak here because you have a very rapid change in the voltage on that rising edge. And there are expressions, of course, where you can look up the capacitance of two wires from an arbitrary diameter and arbitrary spacing. So capacitance is not always a good thing. It can create unwanted noise or signal crosstalk in circuits. The general idea to get around this we draw from our understanding of fields. We know that capacitance is essentially related to the coupling of the electric field lines. If we put a ground plane on, electric field lines that would have connected these two will get dumped into the ground plane instead, and they don't couple the two structures together. And so this is a way to minimize the capacitance by basically dumping the electric flux lines that connect two structures to ground or giving it somewhere else to go. using a fairly simple mathematical expression based on the capacitance of a parallel plate capacitor, we found out that we could represent the energy in an electric field as 1/2 epsilon E squared, and this is an energy per unit volume that's stored in an electric field. We covered very briefly that you can't really store very much energy in here. If you have an electric field strength of about 1 megavolt per meter, which remember happens to be the voltage where air breaks down, you try to store more energy than that and you'll basically get a spark and destroy all your energy. Well, you don't destroy energy, you just basically turn it into heat and light. The amount of energy you can store in terms of energy density in joules per cubic centimeter is very small compared to something like a capacitor, which is small compared to a battery. Even batteries don't store a lot compared to things that burn like wood and gasoline. And of course, nuclear sources like uranium or the deuterium-tritium fission give you absolutely ridiculous amounts of energy. Overall take-home message: energy storage in electric fields is not a very efficient way to store energy. We also looked at materials that conduct electricity, called conductors. And in these materials, you typically have free charges that are almost always electrons that are able to move. And if you allow charges to move, they're always going to move in a way that makes the energy of the system the smallest. And so in metals, which are our most common conductors, the electrons are the ones that move, and the positive ion cores, shown in this picture here that didn't translate very well to this particular program I'm using, stay fixed. And essentially what you get in metals is you get a separation of charge. You essentially, when you put an electric field on, all the electrons are going to rush over there, and they're going to make the electric field inside this metal object, which is this yellow sphere here, be zero, and they're going to leave a net positive charge on that side. Essentially what that does is it's going to terminate electric field lines in the pattern shown and start new electric field lines. But inside a good metal, the electric field is nearly zero. We learned that we can characterize how well electrons flow in a metal by the fundamental property of conductivity. And so electrons can flow in many materials, and they have different conductivities that can range from very, very small numbers to very, very large numbers over a range of more than 20 orders of magnitude. However, when an electron is moving inside a material, it doesn't just zip along in a straight line. It actually has collisions with the vibrating atom cores. The hotter the material, the more collisions it has, the slower the electron goes, and it follows a path that looks kind of like this. It sort of bumps from place to place to place and moves in the general direction it feels forced by the electric field, but that walk is sort of more of a bumpy, random walk. And using a model of how this moves, we talked in the lectures about how we can basically calculate the conductivity, which is given by this expression right here. You can go and look up what those variables mean in the other video. And we saw we could essentially relate the electric field inside a material through the conductivity, sigma, to the electric field. And so one of our fundamental expressions is the current density, J, the amount of charge flow per unit area, or current per unit area, is equal to the conductivity times the electric field. So we've related the flow of electrons and current to the electric field, or the forces we put across a conductor to make the electrons move. This led us to define another fundamental electrical property of materials that is dependent on the geometry and how a device is structured, but is independent of the current and the voltage, which is the conductance or the resistance. And conductance and resistance are just inverses of each other. And they're distributed properties of materials. And resistance, the idea of resistance, relates the voltage difference at any point to the current in a conducting structure. A resistor, in particular, is a device that's designed to have a particular resistance. And we learned how to calculate the resistance. In the general case, if we define the current essentially as the current density per unit area, or sigma E per unit area, and we define the voltage by essentially the line integral of the electric field, we come up with an expression like this that can calculate the resistance of a substance that has an electric field on it at any point in space. And we saw we could define resistance very generally as a distributed property of electrical things using this expression. We also saw that we could calculate particular values or structures that we want to use as resistors. The most common one is we think of a cylindrical conductor that has some cross-sectional area A and length D, and we can come up with a nice expression for what the resistance of this might be, which is this term right here. But this really is a special case of our more general expression right there. We know that when we have a voltage and a current flowing, we dissipate some power, we lose energy, and so we also saw that we can define power loss as a distributed property once we define conductance and understand resistance and can relate voltage and current. It wasn't really covered in the video, but anytime you have power loss, you create heat. So we can think about the local heating of a structure by understanding the electric field within a conducting structure. This is actually becoming increasingly important in electrical engineering. As we go to smaller and smaller device sizes, it turns out that heating effects and power dissipation play a big role in how we design very effective structures. And so understanding electric fields and electromagnetics is one way that electrical engineers need to sort of expand their toolbox. Now, once we defined the idea that we have currents or we have charges that move, we had to take into account relativistic effects due to Einstein's special relativity. And what we looked at specifically was the Lorentz-Fitzgerald length contraction. In other words, if you're moving along at some fraction of the speed of light, space shrinks in the direction you're going. Things tend to compress. Again, this is nothing we ever see in real life because we never move at near relativistic velocities as human beings. But it turns out because electrons feel very strong forces and have a high charge to mass ratio, they can get accelerated to semi-relativistic velocities fairly easily. And when they do, what they see is that if they're moving along by themselves, everything looks normal. They don't feel any extra forces. But if they're moving along near other moving charges, then you get this weird differential compression of charge. And we looked at how oftentimes you get a compression of negative charges inside a wire. And we basically illustrated that by looking at these cylinders and said this is going to be more compressed than the positive charges were. Go back and look at the video where this is explained more. But essentially what the relativistic effects did was they said we need to introduce a new force field that takes into account the compression of some types of moving charges, and that the only time this force field appears is when you have one charge moving in relation to another charge that's also moving. So we have a whole nother set of expressions that essentially relate moving charges to moving charges that in some ways are very, very different than what we calculated with electrostatics. And it turns out that these are the magnetic fields. They really come from the exact same effect, which is the idea that some kinds of matter have a property called charge, but magnetic fields don't go in straight lines. They go around wires, as shown by the green arrows here. They only affect moving charges and are only caused by moving charges. And we learned in the first section on magnetic fields that moving charges that have a velocity v in a magnetic field B, or magnetic flux B, see a force, and that the forces also can be represented by current in a wire. We also learned the right-hand rule, given by these pictures right here, that whenever we have a cross product, we can essentially calculate the forces by moving the fingers of our right hand. Whenever we have a current flowing in a particular direction, if we curl the fingers of our right hand, the curled fingers give the direction of the magnetic field if our thumb points in the direction of the current. Again, this is really tough to explain well in a brief summary, so go back and look at the video about the origin of magnetic fields if you want to understand or review where this came from. Now, once we understand that the magnetic field is really just the electric field in the case that you have moving charges, we introduced the Biot-Savart law, and this was essentially the observation that in magnetostatics, or currents that don't change with time, that create magnetic fields that don't change with time, instead of the charge being what generates these fields, it's current elements, little tiny slices of current that essentially play the same role as the charge does. So Charges create electric fields. Little tiny slices of current, little sort of elements of current, create magnetic fields. The overall magnetic field is basically just the sum of all the little pieces of magnetic field created by these little current elements. So the piece of a magnetic field, dH, is given by this expression right here. Here you have your current element, and unfortunately you have a cross product with essentially the vector that points from the current element out to the place you want to measure the field, which is basically Rm minus Ri. That's that vector right there. It looks very similar to Coulomb's law. You've got the same 4 pi term in the denominator, as well as the magnitude cubed of that vector in the denominator. This makes a lot of sense because really both result from charges. Magnetic fields just result from moving charges. It turns out that superposition holds for magnetic fields, as you would expect, just like it does for electric fields. So if you have a long wire or a curved wire, essentially what you have to do is you have to sum up all the little tiny current elements that make your current distribution. You can do it along a line, you can do it along a surface, or as this integral shows, the most complicated cases when you have current that flows over a complete volume, and you have to sum up the current density over the complete volume to get the magnetic field at any point in space. Again, we learned that these are very, very complicated integrals to do because whenever you basically have a current density crossed with something like this, there's a lot of different terms. You actually have 12 separate integrals or 12 separate triple integrals you're going to need to solve to do this. But it's fairly straightforward. If you can solve the integrals, you can calculate the magnetic field at any point in space. Most of the problems you see, though, have very high symmetry, so these integrals are greatly simplified. Otherwise, the work becomes extraordinarily tedious. Well, we've learned that essentially current elements create the magnetic field through the Biot-Savart law. We've also learned that magnetic fields go in loops around a current element. So if we've got a little current element, that's the black dot there, which we generally represent as I naught dl, the amount of current, times the little tiny differential length dl that points the current in a direction. We get magnetic fields that go around it. Once we have this picture, we learned a couple things. We learned that if we do the trick we did with Gauss's law and start to draw boxes and ask whether flux vectors go more out, go more in, or have an equal amount of going out and going in, there's absolutely no place on this diagram that we could draw a box and have arrows going out or in. What this means is that the divergence of the magnetic flux is always equal to 0. This is interpreted as there being no such thing as a magnetic charge, which makes sense because magnetic fields aren't created by magnetic charges. They're created by moving electric charges. That's fairly straightforward, and it's really just the same force except for moving charges. We also found out that if we basically take the surface integral around one of these boxes, we sum up that side, that side, that side, and that side around any box, that the sum around the perimeter is going to be equal to the current enclosed, and it turns out that this box right here is the only one that has any current inside it. And we call this Ampere's law. And essentially what we did is we then went and explored a differential operator called the curl, which is this del operator crossed with some vector field, and we call that Stokes' theorem. And we learned we could basically, by Stokes' theorem, know that the integral around any contour line in a vector field is equal to the curl integrated over the area of that box. That's Stokes' law right there. And that essentially allowed us to relate the current to the curl of the magnetic field, and we expressed that in differential form right here. And we talked a little bit about how this is very useful when you're calculating distributed fields and you can define differential operators, but it doesn't help you much with homework problems where you really need to use the integral expression operators. The curl, on the other hand, is a very useful expression because it essentially calculates the swirliness of a vector field. The way you think about the curl is you think about dropping a little tiny paddle wheel into a vector field and you ask, does the paddle wheel spin? If it does, wherever you drop it, then the curl is non-zero. The direction of spin is going to tell you the magnitude of the curl, And we think about the direction of a paddle wheel being the axis the paddle wheel spins on. So this paddle wheel right here has an axis pointing up. And so the curl essentially will calculate how the paddle wheel will rotate to get the maximum spin if it spins at all, and the vector that points along the axis of the paddle wheel tells you which way the curl of the vector field goes. Stokes' law and curl allowed us to create a triangle relationship for elements of magnetostatics, just like we had for electrostatics, where we could relate the current elements, that's the generating part of the magnetic field. Remember, magnetic fields are generated by current elements, magnetic fields and fluxes, and we also defined something called the vector potential, and we'll talk about that next. But the general idea here is just like with electrostatics, we have integral type operations as well as differential type operations that connect currents to fields and fluxes to the magnetic vector potential. And this allows you, if you have one, to convert to any of the others if you can do the mathematics. We have this other added condition that there are no magnetic charges, or the divergence of a magnetic flux or magnetic field is equal to 0. Now, one of the hardest things to understand in learning magnetostatics is the magnetic vector potential. And it turns out that the vector potential actually is a real physical quantity that can be measured, but at least I don't know of any really simple, intuitive explanation that's useful for electrical engineering, like there is for voltage or electric potential. We could define the electric potential or voltage as the potential energy of a charge in an electric field, and I don't know that magnetic vector potential has that kind of explanation. If there is one, I don't know it. So it turns out that in electrical engineering, the vector potential is really mainly an aid in calculating magnetic fields. We use it a lot in calculating patterns from antennas. And the reason for this is if you want to calculate the magnetic field, you've got a cross product of two vectors in the numerator and the cube of the magnitude of two vectors, or the difference between two vectors, in the denominator. And these can be really hard integrals to solve. The expression for the magnetic vector potential, the vector potential, is much simpler. You only have one vector in the numerator, and the magnitude term basically is to the power 1 in the denominator. So if you can calculate the vector potential, you can basically convert to the magnetic flux vector by taking the curl of the vector potential using this relationship. And there are certain situations in which that's an easier way to calculate the magnetic field. Particularly, you can define Poisson's vector equation the same way we did for electrostatics, which may also help you calculate this and then go to magnetic fields. For most homework problems, the symmetry of the problem is so high that this is not an efficient way to do the calculation, because always for differential operators you need to know fields or potentials over regions, not just at one point in space. But for doing numerical type calculations, the vector potential is extremely useful. We very briefly covered magnetic properties of materials. We noticed that materials essentially have a permeability that's the magnetic equivalent to the permittivity we defined for the electric fields, and that unlike electric fields and dielectrics that had a permittivity, materials of high permeability tend to concentrate the magnetic field. And that's shown in this diagram that I copied from a Navy training course that shows the magnetic field of a magnet. And if we put an iron bar there, which has a very high permeability, you can see it really sucks in these magnetic field lines and steers it in a different direction. It turns out that a very good first approximation is that materials are magnetic or they're not magnetic. They either have very high permeabilities on the order of hundreds or thousands or even hundreds of thousands, or they have a permeability very close to the permeability of free space. And materials like iron and steel and certain alloys and nickel have high permeabilities. Things like aluminum, copper, air, water have permeabilities so close to that of free space it doesn't really matter for most situations. We also very briefly covered the magnetic boundary conditions. It turns out that the magnetic boundary conditions are almost equivalent, or in fact are equivalent to those of the electric case, except that we substitute the magnetic field H for the electric field and the permeability mu for the permittivity epsilon, but we also see that magnetic fields can change direction when they go into high permeability materials, which essentially accounts for the steering of the magnetic fields we saw right there. We wrapped up our discussion with Faraday's law, which I won't go into, but we also talked about the property of inductance, and it turns out that inductance is the third of our sort of distributed properties of circuits that relates within any kind of electrical structure the magnetic flux to the current that's flowing through the structure. And just like resistance and just like capacitance, it doesn't depend on the magnetic flux or the current. Instead, it depends on the geometry and the materials that the structure is made out of. And just like with capacitance and resistance, it turns out that all electrical structures have inductance, which is a distributed property that's dependent on the geometry of the structure. And inductance, the distributed property, is very different than an inductor, which is an electrical device that's designed to have a specific inductance. And generally when we talk about inductors, we talk about coils of wire or loops of wire. And we do this because coils of wire and loops of wires have a very high magnetic flux for a relatively small current, which allows us both to get big inductances and to control the inductance accurately. It's not at all surprising that if we define the electric flux as the flux vector B integrated over surface and the current through Ampere's law, or essentially the magnetic field around some closed loop, that we can define an integral expression for the inductor, very similar to the way we did for capacitance and resistance. So once we know the magnetic field at any point in space, we can calculate the inductance of a structure. Again, this isn't something you would do typically in a homework problem as much as you would if you were doing a computer program and had to calculate the inductance of a transmission line structure for some odd geometry. It turns out that the inductance of many structures has already been calculated for you, and you can find them in textbooks or amateur radio handbooks. Very briefly, Faraday's law related the change in magnetic flux to the voltage around a loop of conducting wire, and Faraday's law leads from inductance into our basic circuits relation that the voltage is the inductance times the rate of change of the current. Again, inductance is different than an inductor. An inductor is a device that's designed to have a specific inductance, and as we've said, if you want to make an inductor, you essentially determine a coil, choose the diameter, wrap a certain number of turns to get the inductance you want. If you need to have a higher inductance, you put a high permeability material in there, because remember, the high permeability material is going to suck up these magnetic lines and concentrate them very highly and increase the flux going through the structure and thus increase the inductance. If you slip something like a piece of ferrite into a coil of wire, you increase the inductance often by a factor of 10. Just like capacitance, you don't always want to have high inductance, because inductance essentially couples through the magnetic flux two currents. Let's call it basically a current I1 over here and a current I2 over here. They can couple the two conducting structures together. That current I1 creates a magnetic field that couples to line 2, or if you have a circuit that you want to be very quiet and not have a lot of noise on it, if you have stray magnetic fields, say your circuit's near a transformer or an AC power line, the magnetic field put out by those other currents will couple noise right onto your circuit. And so you don't always want to have a high inductance. Ways to increase the inductance are simply to decrease the inductance, to minimize it, or simply to decrease the amount of flux. So you can just basically move these lines closer together. That's going to decrease the area magnetic field can couple to. Disadvantage is you increase the capacitance by moving it closer together, so maybe it doesn't work so well. Another way that engineers do this a lot is by creating wires called twisted pairs. This is essentially where you think of a wire as being a small loop, and essentially if you do a 180-degree flip of the wire, every once in a while the voltage induced on one loop of wire is canceled out by the loop on the other, and you'll see this a lot of times in many telephone and Ethernet cables. And that's pretty much the high points and the big ideas for magnetostatics and electrostatics. I've gone through this very, very quickly. This is really more of a review lecture. If you want to go into the details and look at more how these things are derived and more of the meaning, go back and watch the earlier lectures.